So we're going to talk about the idea of continuity. Continuity means, can you trace the graph with your pencil without lifting up your pencil from the paper? So can you draw this in one shot? Or you have to draw it in different pieces is the whole idea. Okay, so continuous. So, okay, first of all, let's just draw some XY coordinates. Okay, continuous means you can draw this graph with one stroke without lifting up your pencil. So something like this. That's called continuous. Okay, you can draw it without lifting up your pencil. If it's not possible, we call it discontinuous. So we have two kinds of discontinuity. One is called non-removable. The other one is called removable. Okay, so non-removable means like no matter what I do, I cannot fix this discontinuity. So something like this. So I have to draw two pieces, and there is no way to connect them. Does that make sense? Okay, removable means that it is discontinuous, but maybe I can connect it. So it's kind of like this. I draw this part, there's a gap, and then I continue. So I have to take my pencil off to redraw the second part because there's a gap. But when we draw this in math, we don't want to draw a gap like this because it's very confusing. Like, did you just forget to draw it or you meant it to look like that? So we draw a hole like this to say that there is a gap there. Okay, so we're going to talk about these two kinds of discontinuity. One is non-removable. Non-removable means there is no way to fix this. Removable means if I just put a dot in here, I could fix it. Can you guys remember the difference? No.
Yes.
Okay, removable means I can remove it. Remove this discontinuity and then it would be connected.
Yes.
I
understand.
You understand, thank you. Someone was shaking their head, so that's why I'm re-explaining. Non-removable means there is nothing I can do to connect them. There is no way. Like I can't connect them like this. It's just no way. So non-removable. Okay, so discontinuity. What causes this discontinuity? Basically, whatever makes the denominator undefined. So your domain restriction, all of it. And we also call this points of discontinuity. Okay, so two kinds, non-removable, removable. So we are always looking for what makes the denominator undefined. Okay, so first is non-removable. Non-removable means vertical asymptote. So all the stuff you did last night were non-removable. This is when the discontinuity factor in the denominator does not cancel with the factor in the numerator. Okay, let's look at an example first. First one, x minus 3 over x minus 1 times x minus 5. Where are the points of discontinuity? What? Huh? 1 and 5. Yeah, only the denominator. Does the factor in the denominator cancel with anything in the numerator? No. So then these 2 points are both non-removable. Discontinuity. Okay, let's try another one. The second one. Where are the points of discontinuity? What do you have to do first? Factor, yes. Oh, wait, I did this wrong. Okay, so where are the points of discontinuity? Did I factor wrong? Oh. Oh, sorry. Okay, so where are the points of discontinuity? 1. Okay, does it cancel with anything in the numerator? So what kind of discontinuity is it? Yes. Okay.
Is there a faster way to write those two ones?
I don't have any. Okay, now when a removable or when a discontinuity or the factor does cancel with the numerator, we call that a whole. Non-removable, I cannot fix it, vertical asymptote. If I can fix it, it's going to be a hole in my graph. Okay, so this is when the denominator cancels with a factor in the numerator. And this discontinuity is temporarily removed. We call this a hole. All right, so let's go ahead and look at this question. Where are the points of discontinuity? Huh? What? Say that again?
X equals -1.
Yeah, -1. Where is the hole? Well, which factor cancels with the numerator? Okay, so where's the hole? X equals -1. So this is called a removable discontinuity. Okay, so kind of hopefully this is a quick recap. Non-removable asymptote. Removable, a hole. Okay? Removable also means you can remove the factors. Does that make sense? Because they cancel, so they got removed. All right, this one. What do we have to do first? Factor. Hopefully I don't factor wrong this time. Sorry. Okay. All right, where are the points of discontinuity? 3 and -1. Anything in the denominator, they're all problems. We just need to categorize them. So everything in the denominator are going to cause discontinuity. They're going to cause different discontinuity based on what kind they are. Okay, so is there anything that cancels?
3.
Yeah, x minus 3. So then x equals 3 is what kind of discontinuity? Removable, because I removed the factor. What about x equals -1?
Non-removable.
Yes, non-removable, because I didn't remove it. Okay? Everything in the denominator is a problem. What kind of problem is it? Depends on whether it gets canceled or not. Oh, let's see. Okay, next page. All right, we're now ready to bring all the stuff we learned yesterday to this thing. You have a question?
Yeah, so the x equals -1, the non-removable, that would be the whole.
No, anything that's not canceled is gonna be an asymptote.
So would we write that like usually?
Depends on what they ask you to do. So we'll do an example together. Okay, so we need to basically do everything we know about this. All right, again, what is the first thing you do? Factor. X plus 3. Okay, this is x. Now I'm scared of my factoring. -1 minus 3. Okay. Domain. What is the domain? X is cannot equal to 3 and 1. Yes, correct. Points of discontinuity. Where are the points of discontinuity? Yeah, x equals 3 and 1. So everything in the denominator. What kind of discontinuity is 3? Non-removable, and then 1. Yeah, both of them are non-removable. Nothing canceled, right? Okay, x-intercept is kind of hard to solve, so let's solve y-intercept. Y-intercept is when what happens? X equals 0. So y equals 0 plus 3 over 0 squared minus 4 times 0 plus 3. 1. I'm going to tell you a quick way because you guys are pretty bright. All the x's are going to be 0. Just look at the constant. Okay, so the fastest way. All right, x-intercept is when what happens? Y is 0. 0 equals x plus 3 over x squared minus 4x plus 3. How do I solve this? Multiply by the denominator, which will give me just 0. Right? 0 times everything is 0. Yeah? Okay, let me write that. Okay, so, I would multiply everything by the denominator, but that's kind of a moot point. Everything times 0 is just 0. So 0 equals x plus 3. So x equals what? Negative 3. Okay, so that's the x-intercept. Are you guys good? Yeah? Okay. All right. Try this one. What is the domain? This is a trick question.
Well, it can't be.
So what's the domain? Someone said it. Yes, all real numbers. Because it's impossible to make x squared negative 1. Unless it's imaginary, which is not going to be on my graph. So then this is going to be all real numbers. Points of discontinuity. Oh, you have a question? No, someone has a question? No, you're okay? Okay. Where are the points of discontinuity? None. If your domain is everything, then you shouldn't have a discontinuity. Okay, let's try y-intercept. See if you guys can just do the trick. Where is the y-intercept? 5. Negative 5. Okay, x-intercept is when y is 0. 0 equals x minus 5 over x squared plus 1. 5. All right, I'm going to tell you the fastest way to solve for x-intercept. Yes, always the numerator, because the denominator always does not matter. So, are you guys ready to try one yourself? Sure. Okay, so number 3, this one does have a hole. So please be careful. So go ahead and do everything and then let me know when you're done. Okay, what is the domain?
X can't equal
4. Where is the point of discontinuity?
X equals 4.
What kind is it?
Removable.
Okay, where is the y-intercept?
That
1. Okay, and x-intercept. This is a little tricky. So hopefully you did factor. I'm sure you did. That's why you noticed that it was removable. Okay, so this got removed. So x-intercept. X-intercept is when the function is equal to 0. So that means you make this whole thing equal to 0 and you try to solve, right? Now this is a little bit tricky because when you do try to solve, you're going to get x minus 4 and x plus 1. So you would say x-intercept is at 4 and negative 1, which is incorrect because this is a hole. At a hole, nothing happens. So then you have to jump over that number. So then, yes, the function would have crossed the x-axis at that point, but instead of an actual point, there was a hole. So then the actual x-intercept is only at negative 1, 0. So to kind of summarize, what you want to do is simplify the function first and then make it equal to 0. So this is a very tricky part, the x-intercept. You got to simplify the function and then make it equal to 0. Because if you don't, you might make the whole the x-intercept when it's actually telling you there's nothing there. Okay, all right, let's go on. Oh. Okay, vertical asymptote. So vertical asymptote is the vertical line or vertical, oh, I'm sorry. I think I meant to say the, oh yeah, vertical, invisible line that the graph cannot cross. It really, really cannot cross. If you try to cross it, you know, definitely I will take points off. So this is only when the denominator does not cancel with the numerator. So that's vertical asymptote. So all the things you graphed yesterday were vertical asymptote. Nothing in the denominator cancels with the numerator. That's the vertical asymptote. The second one is the horizontal asymptote. This is the horizontal invisible line that the graph does not cross at infinities. Infinities means the two ends. So sometimes near the origin, it does cross. So don't be alarmed if it does cross. It happens, but at the end, the two ends, it's not going to cross. So please be careful of that because eventually we're going to graph things that does cross. So don't be like, oh my gosh, I'm supposed to not make it cross. Sometimes it does. Okay, horizontal asymptote is a little tricky. There are three cases. When we talk about three cases, we're talking about the function is a polynomial over another polynomial. So when the degree in the numerator is equal to the degree in the denominator, the horizontal asymptote is the ratio of the leading coefficient. Okay, we have a lot of vocab here, so let's talk about vocab. Let's say the function is 3x minus 1. What is the degree? 1, yeah. Degree of the degree of a function is the highest exponent. So that's what it means. When it says degree, it's the highest exponent. Okay, next. What does leading coefficient mean? 3. The number in front of the highest power. Okay, the term that has the highest degree, that number in front, the coefficient is called the leading coefficient. Let's just talk about 3x minus 1 for now. Then you didn't simplify your function. Yeah. Okay, what does ratio mean?
Something the fraction.
Fraction. All right. So when the degree of the numerator is the same as the denominator. All right, let's look at this case. So what is the degree of the numerator again? 1. What's the degree of the denominator? 1. So are they the same? Yes. So it tells me that if they are the same, the horizontal asymptote is the ratio, so fraction, of the leading coefficient. 3 over 2. Can you guys see that? Leading coefficient 3 over 2. So that tells me the horizontal asymptote, remember horizontal asymptote is a line. So this is going to be y equals 3 over 2. Okay, y equals 3 over 2. Case number 2. When the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is 0. Okay, what's the degree in the numerator right now? 1. What's the degree in the denominator? 2. So 1 degree is smaller than 2 degrees, it's automatically 0. Okay? If you really want to know why, I can tell you why, but we're going to learn about, we're going to learn about why a lot next year. Okay, the third, okay, so, forgot to write this here. Okay, so when the degree of the numerator is bigger than the degree of the denominator, there is no horizontal asymptote. Instead, there is a slant asymptote. We're not going to solve for the slant asymptote this year, but we'll do it next year. So like for example, this one, degree in the numerator is what? 3. What's the degree in the denominator? 2. So 3 is bigger than 2. There is no horizontal asymptote. None. Okay, let's apply. Find the vertical and horizontal asymptote. Vertical asymptote is the problem in the denominator when it does not cancel. So where is the vertical asymptote? X equals 3. So whatever is in the denominator is the problem. Horizontal asymptote, we need to check what? Degrees. Very good. So are the degrees the same, bigger on the top or smaller on the top? Same. So then if it's the same, you check leading coefficient, the ratio. So what's the ratio? 2 over 1. Yes. So it's just y equals 2. Okay, next one. This one we need to factor. Okay, where are the vertical asymptotes? 3 and -1, because it doesn't cancel, right? Where, oh, okay, horizontal asymptote, we need to check degrees. Is the degrees the same, smaller, or bigger?
Smaller.
Smaller, so what's the horizontal asymptote?
0.
Yes. All right, this one, let's have you practice. All right, let's finish this one. So the vertical asymptote is at x equals plus minus 2, and y horizontal asymptote is y equals 1. All right, now let's put everything together. Domain x is not equal to 2 or -3. They're both non-removable at x equals 2 and -3. X-intercept is at -6, 0, and y-intercept is at 0, -1. Vertical asymptote is 2 and -3. Horizontal asymptote is 0. Questions?